Welcome back to Electrical Point. In the last video, I have discussed the classes of motor duty in great detail. Today, we will discuss the determination of motor rating based on the type of duty cycle. Okay, this is a very important topic from the exam point of view. You can expect at least one numerical question from this topic in your final exams. Okay, in this video, we will mainly discuss the equivalent current, torque, power method for variable load. Okay, in this method we consider that the cooling and the heating condition of the motor is same. Okay, therefore this method has some limitations. The method is only applicable when the motor runs at constant speed or forced ventilation is used. Whenever these two conditions is satisfied, either of these two conditions is satisfied, you can use this method. Okay, when motor runs at constant speed, the constant losses will remain same in the motor. Therefore the cooling condition will also be same. Okay, even if we apply natural cooling, natural ventilation, then also the cooling condition will be same. And if the motor does not satisfy this condition, then we will check if forced ventilation is used or not. If forced ventilation is used even if at lower speed, the cooling condition will be same, the heating and cooling condition will be same, and we can use this method. Okay, therefore when you attempt a question where you are asked to determine the motor rating, first check if these two conditions are satisfied or not. If one of these conditions is satisfied or not, if you see that the motor runs at constant speed or forced ventilation is used, you can use this method. Okay. Now let us discuss the method. We have a load profile like this. Here I1 is the load current for T1 interval, I2 is the load current for T2 time interval. Similarly, IN is the load current for Tn time interval. Okay, now the aim of this method is to find an equivalent current IEQ or an equivalent torque TEQ, tau EQ, or an equivalent power PEQ that produces the same average loss. Okay, this produces the same average loss that will be produced by these actual variable currents. Okay, this is the aim. We have to find the IEQ. In most of the question that you will get, you will be given the torque profile and you have to find the PEQ. Basically we will discuss these questions in the upcoming video, but in this video we will deduct how we can determine the IEQ. Okay, the method to determine the tau EQ or PEQ is same as that of IEQ. We'll discuss those things. Now we know that motor losses have two components. Okay, motor losses have two components. One is constant loss PC that does not change with load condition. Okay, this is same. This is the core losses, friction losses, etc. Core loss plus friction losses, etc. This remains same even if the load current is different. And the another is variable loss. You can see from here that this loss changes with variable current. Okay, now the average loss that is produced by this current profile I1, I2, I3 up to IN will be, for I1 current the loss will be PC, that is the constant core losses, plus the loss produced by the current I1 square R. This loss is there in the motor for time duration of T1. Okay, now for T2 similarly we will have PC plus I2 square R T2. Similarly we will also have for I3 up to in PC plus in square r into tn for tn time interval. As I have already said that the aim of this method is to find the average loss, same average loss. Therefore, the average loss will be this value divided by T1 plus T2 plus T3 up to Tn. Okay. Now we'll further solve this thing. You can see from here that PC will come out as PC T1 plus PC T2 plus PC Tn, and the time will be cancelled out by this term. Therefore we'll be left with PC plus this value will remain same, I1 square r T1 plus I2 square r T2 plus n square r Tn divided by T1 plus T2 plus Tn. Okay, this is the value. Now if we further solve it, Tn up to in square Tn multiplied by r. Let us assume that the value that we get from this is A. Okay. Equivalent current, that is IEQ, that will produce the same loss, which will be equal to A. Okay. Now the IEQ current will produce a loss of PC. This will remain same plus IEQ square R, which must be equal to A, or you can say PC plus IEQ square R. A is from the previous slide PC plus up to Tn I1 square T1 up to In Tn. Now if we compare the left hand side with right hand side, we will get that IEQ is equal to under root Tn in square Tn. Okay, this is the equation that we will use to solve the questions. Okay, now in most, as I have already told that in most of the question you will be given the torque profile and you have to find the power rating of the motor. Okay, this is basically same as the IEQ, because in those motors where the torque is directly proportional to the load current. The example of such motors are shunt motor, shunt DC motor, or you can say separately excited DC motor. Separately excited DC motor. When the name of such motors will be given in the question and the torque profile will be given, we will find the torque equivalent similar to this IEQ. Okay, and then we will find the power from the torque. Now you can say that torque equivalent is same. Tau 1 square T1, tau 2 square T2 up to tau n square Tn. Similar equation we will get for power also, as we know that the power is directly proportional to torque in such motors. The torque is directly proportional to I, that is the load current. Okay, now we have found the IEQ or tau EQ, or we can say power equivalent. Okay, we have found this value from the load profile. Now we have to find the rating. For this we have few rules which we will discuss in the next slide. Okay, now after IEQ or torque equivalent or power equivalent is calculated, we follow the following steps to determine the rating. Okay, first step is select a motor with the next higher current rating that is available in the market. Okay, and we designate this value as I rated. Now we know for DC motor, remember these steps are very important. For DC motor, what happens is that basically we can motor can be allowed to carry a larger current than the rated current for a short duration, as the temperature rise is not instantaneous. Therefore the motor can carry a higher load than the I rated. That higher load is suppose I max, that we will get from the load diagram. Okay, in the previous slide we have see that suppose this is the load profile, okay, of a motor. This one is I1, I2, I3 and I4. Okay, from the load profile you can see that I2 is the maximum load that the motor will carry during this period. Okay, therefore Imax will be I2. In this case Imax will be I2. Now what I have told that the average, the rated current will be less than Imax, and for DC motor the limitation is 2. So what we will do, we will find a value lambda. This lambda is Imax divided by I rated. Imax is the maximum load current that the motor will carry during the load cycle. Okay, for this case this is I2, and I rated is the rating that we have already selected in the first step. Okay, now if this value is less than 2, less than or equal to 2, then the selected rating of the motor will be I rated. Okay, if it is more than 2, if the lambda is more than 2, then we have to go back to step 1 again and select a higher rating, I dash rated. Okay, this is more than I rated. Now again we have to find the lambda dash and compare to 2. If it is less than 2, then it's okay. If not, then again go back to 1. We'll discuss all these steps in the next video when we will solve problem related to determination of motor rating. Okay, now for induction and synchronous motor, we define a value lambda dash which is same as that of lambda only. This is tau max, the maximum torque, divided by rated torque, and the values are for induction motor lambda dash must be between 1.65 to 3, and for synchronous motor the value of lambda dash must be between 2 to 2.5. okay, These are the condition. We will use both this lambda and lambda dash condition while solving the problem in the upcoming video. That's it for this video. Do like, share and subscribe the channel. Stay tuned. Thank you.